Hi, our last speaker for the session will be Raymond Hettinger with Super Considered Super. Please welcome him.
How are you all doing? How many of you read my blog post, Super Considered Super? Then why are you here? Or how come you're not over at David Beasley's talk or Titus Brown? Or now, I will tell you some things that are not in that blog post. I will tell you about how to use Super for dependency injection, which is one of its magic superpowers. One of my goals here is to make sure that you know what Super really does, that you have a good mental model for it. I could give you a series of rules for using it well, but I'm going to try an experiment. I'm going to get 3 volunteers from the audience, one of whom tried to unvolunteer but is now in. And we'll conduct a little experiment up here. And the experiment is, if we work out visually what Super does, will you be able to remember it? I believe the answer will be yes, with a live demo of people as classes. So we'll learn what Super really does. Then we'll do some magic with it, something that I'm sure none of you have ever done before, a death-defying act. We will use Super for dependency injection. How many of you even know what dependency injection is? Who's ever used Super for it? I'm astonished that I even got a 1. So that's new. Okay, and then Super was introduced for a particular reason, which is cooperative multiple inheritance, which is really a fantastic idea. There's a lot of research behind it, but when it started out in Python, it wasn't particularly well documented. So a person went and tried it out. And they tried it one way, and they tried it another, and they tried it another way, and every way they tried failed. So they wrote a blog post, Super Considered Harmful. How many of you have read that? Then why are you here if Super is bad for you? And I think the problem with that article was a person said, I tried out several ways to use it, and it didn't work, therefore you shouldn't use it. As opposed to what I believe is the correct perspective is, are there some things I need to know in order to get it to work and do all of its magic? And the answer is yes. And I'll tell you what those 3 things are. So that's what we're going to do here. I'm taking a risky approach. I have no slides. I have live code, and I'm going to run it on screen, and we'll edit and modify some of the code for you. What could possibly go wrong? I'll also do it in Emacs. What could possibly go wrong? I'll get volunteers from the audience who I didn't know before today. What could possibly go wrong? But remember, you can always go over to Beasley's. Okay, all right. All right, so now you know what our goal is. Inheritance is really easy. Inheritance is a tool for code reuse. The whole idea is there's code in some other class, and instead of copying it into your class, you want to reuse it. So when one of your clients, an object, calls you, you can either do the work yourself, or you can hand it off to someone else who knows how to do the work. So if somebody asks you what inheritance is for, don't give a Java answer. It doesn't have to do with abstract base classes or whatnot. What's inheritance for? It's a tool for code reuse. It lets one class use the code in another class. And how hard could that be? Not very hard. I'm just going to ask somebody else to do the work. If I'm a company, and one of my customers calls me and orders a product, I ship them a product. Do they presume that I did all of the work myself, or could I subcontract? Big companies have subcontractors. They have suppliers. Is the supply chain visible to the customer or not? Traditionally, the view of interfaces is, no, it's not visible. Well, I'm going to ask you to alter your worldview a little bit and say who the supplier of a company is that matters. So let's say you have some company you hate. Let's say they have genetically modified seeds or something like that. And you have a restaurant that you like, and you find out they get their food from that restaurant. Does the supplier matter to you? It does. It's part of their chain. So even though your contract with them is, I order some food from you, you give me some food back, and that's the full relationship. But in fact, there's another part of the API is, who are your suppliers where you're getting your seeds from? Fair enough. And so I'm going to treat that as part of the API, a reprogrammable part of the API, something to where we can do dependency injection, to where you can go to your favorite restaurant and say, I'd like to order my favorite food, but get it from someplace else. You see where we're going with this? What is inheritance for? It's so that one class can reuse the code from another class, the supplier. What's super going to label us to do? Retarget it. So inheritance is easy. One class uses another. Well, I should put it another way. Single inheritance is easy. Whenever you get multiple inheritance, it could get more complicated, but doesn't have to. What is the easiest way to do multiple inheritance? Inherit from two different classes that don't have any overlapping methods. That also works perfectly. Mix-in classes work that way and are fantastically useful. Is multiple inheritance easy when there's no overlaps? Yep. And inheritance is a tool for what? Code reuse. Okay, I think you get the gist. So, multiple inheritance is easy, single inheritance is easy. What's hard? What if you have multiple inheritance and there's a diamond diagram and the same methods are repeated on either side of the chain? Then it gets harder. How much harder? It took a long, long time for computer science to work this out. And when they came up with it, they have a proof that it is the optimum and best solution to this problem. It's a C-cubed linearization algorithm. What does linearization mean? Make a line out of. Are you guys all sitting in a line? No. You're sitting in a big blob of rectangle of a mob. What if I were to linearize you? Then you would be in a line. Why would I need to linearize you? Because I have a goal. After this talk, I'm going to go shake everybody's hand. I can't do it all simultaneously, so do I have to do it one at a time? Yep. So I need to linearize you. The C-cubed linearization algorithm is a way of taking this blob, amorphous blob, and putting it in a straight line. One calls the other, calls the other, calls the other. What is our biggest problem with super in Python? It's not its design. Its design, I think, is flawless. It's beautiful. Guido did an extraordinary job with it. The problem is the name. It shouldn't have been called super. Why not? The answer is, if you've learned super in any other language, it doesn't do the same as Python. So let me run my survey here. How many of you have used Java? C++? Smalltalk? How many of you have used any language that has super in it? How many of you realize that Python super is not like that at all? What is super in every other language is not Python super. What does it do in other languages? In other languages, it calls your parents. In single inheritance, it's easy. Hey, Dad, can I use a car? Multiple inheritance, it's also easy. Dad, can I use a car? No. Mom, can I have the car? Easy enough. Inheritance, whenever you call super, is about calling your parents. But Python's does something different. It does call parents, but not your parents. When you call super, whose parents get called? It is not your ancestors. It's your children's ancestors. So here's my family tree. I've got Raymond, Ramon, and Gail, my parents. My wife, Dennis and Sharon, are over Rachel, her parents. But Rachel and I have a child, Matthew. So Matthew has a bigger family tree than we do. And it turns out all of our Matthew's grandparents are descended from Adam and Eve. I put those names in just to make it a diamond diagram. So it spreads out and it comes back up, at which point you have a non-trivial multiple inheritance problem. So that's our family tree. You want to go talk to everybody in the family one at a time. What do you have to do to the blob? Linearize it, which means make a line out of. And that's what the MRO does, the method resolution algorithm. So let me turn on that code. And one of the nice things about help is it shows the method resolution order. It says if you have an instance of Matthew, you start with Matthew. If when Matthew calls super, it calls me. When I call super, it calls my dad. But then something interesting happens. When you call super on Ramon, it doesn't go to his parent. Remember, his parent is he's descended directly from Adam. it calls out to the side, which is kind of interesting because my father is about 10 years older than his wife. And so that means that when he was born, his super call went somewhere else other than where it goes now. So his super call, where it went, has changed over time. What is it that changed it? When he was born, none of the rest of the people on here existed. So if you looked at his super code, you might think it called his parents Adam and Eve. And in fact, if he was the starting point, yes. But now that Matthew is born, it's Matthew's inheritance tree that matters, not his. So when he calls super, it doesn't call his parents, it calls one of Matthew's ancestors in exactly this order. So this is kind of shocking. That means whenever you use super, you can't know in advance where it's going to call. Who learned something new? Super calls your parents, right? No, it may call somebody who hasn't even been born yet. Ramon's super calls Gail. Now, Gail's is kind of interesting because her super calls Rachel, and Rachel is far younger than Gail. Rachel goes to her parents, who then call Adam and Eve. And that is the MRO, the method resolution order. The most important thing you learned so far, linearization. It means to make a line out of. It is what order to visit everybody in. What does Python super do? Does it call your parents? No, it calls the parents or ancestors of your children. If you've learned that much, you know a great deal about Python super now. So what should it have been called? Well, given that we've taken this diamond diagram and turned it into a line, the line down here, what super really should have been called is the next in line. So Ramon, when he calls super, it's not really super, it's the next one in the line. Who's the next person in the line after Ramon? Don't leave me all alone up here. All right. Yeah. The next in the line after Ramon is Gail. It's not about calling parents, it's the next in Matthew's line. Does super mean next in line? If you've got that, then you're in wonderful shape. So, where do we get all of the awesomeness from in super? One way is that this line gets computed automatically. Another way that super is awesome is it is the youngest person in the chain, Matthew, that determines what the line is. And you can't know in advance where your super is going to go. This is a good thing because it means your children get to change where it goes. After all, you guys didn't like the supplier of the food at the restaurant you went to. Maybe you can subclass the restaurant and change its order without breaking its interface. Would you like to see that in action? Okay, we're about to uncork a can of super whoop-ass. Here we go. We got a dough factory, and the dough factory has get dough. We have a class pizza, and it only has one method, order pizza. And you call in and order some toppings. It prints it's getting some dough, it makes some dough, and drives on. Originally, when this pizza company was first formed, it made its own dough. But later, it turned out other things needed dough as well. What is a really good tool for code reuse when it comes to classes? That's right, it starts with an inhere and ends with an tense. Right. So what do we do at that point? We take the code for getting dough and we pull it out to our parent class. Remember, inheritance is a tool for code reuse. So lots of other classes can go to this dough factory and get their dough. Have we improved the code? Yes, because we've eliminated redundancy. The problem is this dough factory is hardwired. And if we change the name of the dough factory, if we choose a different dough factory right here, we have to change it in two places. What does DRY stand for? Do not repeat yourself. If I have to say it twice here, am I repeating myself? You all know, that's right. There must be a better way. And the better way is this. Oh, never do live coding. I don't even see my cursor. How is this possible? Okay. Oh, it wants to know if it's changed on disk. How is this possible? I don't know. What does Emacs stand for? Exclusively used by middle-aged computer scientists. Okay. All right. Super. In what way is the code better now? The way that the code is better now is simply that we didn't mention dough factory twice. So if I change to a different dough factory here, Super will automatically be aware of it. That reduced redundancy in our code and makes it awesome. Didn't I mention Super is super? But I know what you're thinking. That's the same way you would use it in every other language that has super. And in fact, you would. Yet, you got a magic power, whether you knew it or not. Let's look in detail at what's actually happening here. Yes, I want to save. I will go run our pizza factory. And what does it do? It goes to get dough. That's the first step in making a pizza. And it calls super. And it goes to the dough factory, gets the dough, and now we're making a pie with some insecticide-treated wheat dough. You guys want some insecticide on your pizza, right? Okay. And we've got pepperoni and bell pepper. Two things good for you, one of them not. How did it work? It called its parent to do the work. Can we see what its method resolution order is? Sure, this is a simple linear inheritance, so we could just run help on the pizza class. And see, the order is we search the pizza for get dough, and when we don't find it, we fall back onto dough factory. Easy peasy. Any questions on that? I hope not. That's pretty easy. There's only one problem with our program, and that's the kind of pizza it makes is treated with insecticide. I know what you're all thinking. There is. There's another dough factory in town. This is the thing I like about the Mac, the whole zooming in. It's an organic dough factory. In fact, it was a subclass of the regular dough factory. And this one gives you pure, untreated wheat dough with no insecticides. Good for you. Here's your problem. Your problem is over here in this class, the dough factory is hardwired. Or is it? It's not hardwired. The magic property of super in Python is the inheritance chain was not determined by pizza. The inheritance chain is determined by your children. Matthew is the one who caused my father to call out to the side to his wife instead of up to his parents. So what we'd like to do is make a child of pizza, a subclass of pizza, that injects in between the pizza place and its supplier, a new supplier in the chain. And it's amazingly easy to do. This is dependency injection with nothing up my sleeves, without changing any of the code on the left side. I will magically improve our pizza. All we do is make an empty class, an organic pizza. Is that a subclass of pizza? Sure it is. Is it also a subclass of organic dough factory? Yes, and the linearization algorithm guarantees that the organic dough factory will go before the pizza factory, which is kind of awesome. So now I'll go order it with anchovies. And without having changed the order pizza, notice that we now get pure, untreated wheat dough. Who thinks that's awesome? You can take anybody who has a supplier and they advertise their supplier as part of their API. It's not actually hardwired, the inheritance chain. It is telling you what the default supplier is. Unless you tell me any different, I'll be giving you insecticide dough. But if you tell me differently, I'll go check the organic dough factory first. This is awesome. It's a magic power of super, and I have not seen that in many other places. Who learned something new? You dig it. So, are any of you even slightly unsettled by this? Why? The reason you're unsettled by it is first you're like, is this fragile? No, it's deterministic. There are precise rules that tell you when you make this subclass, what order you will sort it. Part of the default supplier chain is documented to be dough factory. and you are allowed to change the order. It does this by design. It's not an accident of Super that it does this, it's on purpose. The whole C-cube algorithm was designed so you could do stuff exactly like this. Is it a accident or an on purpose? It's on purpose. The only problem with this example, well, the good part of this example is I think everyone understands it. The bad part of the example is that it's not compelling. Should we do something more interesting with it? A robot. There. Now who's got the coolest presentation, me or Beasley? Beasley doesn't have robots over there. Because his talk is on concurrency, so I presume he's giving his talk and listening in this room at the same time. All right, so we've got this robot. I didn't build it, I bought it. So I don't actually have control over the source code for this robot. Given a tool, it can go fetch it, it can move it forward, it can move it back, and it can replace it back from wherever it got it from. I've just got prints in here, but the actual robot moves every time you make one of these calls, which is unfortunate because that robot is rather fragile and it wears down easily. If you make too many calls with it that are unnecessarily, you're going to wear out your poor little robot. And you wouldn't want a worn out robot, would you? No, that would be a terrible thing. So, how do you specialize your robot? It's a fairly easy thing. You subclass it. Subclassing is used to specialize. And so our extend. We're going to extend the robot by adding a new method, clean. And what clean does is take advantage of the parent methods, and we're programming the robot to use something useful. This is not a toy example. This is a proper way to use subclassing. A parent provides a toolkit, and then the child exercises that toolkit in some complex way. It makes this robot programmable, which is kind of cool. We use super, which is kind of nice. What does this do? To clean something, you fetch the tool, you move it forward and backward a certain number of times, and then you put the tool back. In particular, I'm going to use a broom. And I think you will be rather unsurprised at the outcome. What did it do? Well, it went and fetched a broom, it moved it forward and backward, it swept, and it replaced. Is that pretty darn useful? A sweeping robot. I bet no one's ever thought of that before, Roomba. And how did they design it? They made a general purpose robot, and then they just subclassed it. Easy peasy. So I write this little routine to specialize my robot. Should I test it? Yeah, testing's a good thing, but if I run a test on the actual robot, I'm going to wear it out. What can you do? Well, I want to call this method, but I don't want the real robot to be called. What I'd like to do is have a mock robot called, because my goal is to test the clean method, not to test the robot itself. But it looks like this relationship is hardwired. Cleaning robots are robots. We say is-a, not has-a. Cleaning robot is a robot. And now I don't want it to actually is-a be a robot. I want it to be a is-a mock bot. And so we'll mock up our robot. So let me put the bots side by side. Both of these, the mock bot and the real bot, have exactly the same methods. But what the mock bot does is it doesn't actually do a physical movement. All it does is record all of the calls that are made to it. It appends it to a list of tasks. You can call the mock bot as much as you want, and it won't wear out. All we need to do is go edit this code and force it is to temporarily edit the code, make it use the mock bot, and then switch it back. Good idea or bad idea? Bad idea. There is, and it only takes one line of code. A mocked cleaning robot. It inherits from robot, and it inherits from mock bot. We are guaranteed by the linearization rules that anytime our cleaning robot calls its supplier of robotic services, that it will check for mock bot before it checks the actual robot. And so I can write a proper normal unit test to test clean. If I had this test the cleaning robot, a real robot would be doing the physical movements as it did on the left, of course wearing it out. But with my mock cleaning robot, I can go tell it to clean with a mop, And then I can expect that it gets this output. Let's check it out. I got a dot. Very satisfying. What did you achieve at work today? The dot. Your friends don't typically understand how satisfying it is to get a dot. Thank you, I saw that one. The last talk, I ignored my timekeeper, and the big hook came off, and they dragged me off of a stage, much to the amusement of my audience. All right, so how did this work? Well, very simply, it injected itself into the chain. Run this in an interactive mode. Oh, what version of Python am I using here? 3 point what? You don't have one of those, do you? All right. And let's do help on the mocked cleaning robot. And what I'm looking for is the mocked cleaning robot resolution order, which says it's going to go check for cleaning robot. What will it find in cleaning robot? There, it's going to find a clean method. But if you call some method on it, like a fetch, where does it look next? The meaning of super is next in the MRO, the next in the line. And the next in the line is the mock bot, ahead of the real robot. So the mock robot gets called first. This is dependency injection. It's easy to do. It's one line of code. Make a mock class, inject it just with this. There's nothing fragile about it. It's guaranteed behavior. It's what it was designed for. How many of you learned something new? My work is done. I could get off the stage right now and just declare victory. That would be the smart play. But hey, I've already risked using Emacs on stage. What could possibly go wrong if I just keep on talking? I know. You're thinking these are all contrived classes. Why don't we try something from the standard library? We've got counters in the collections module. What are counters good for? Counting things. They are a subclass of dict. Is a dict an ordered collection or an unordered collection? Unordered collection. So we're going to get counts, but they're going to be scrambled. What else do we have in the collections module that remembers order? Ordered dictionaries. That's fantastic. They remember the order. That's a wonderful thing. Do ordered dicts count? They don't. So you've got a devil's choice. You can have your order or your counting, but you can't have them both, or can you? There is. It's quite simple. I pounded too hard. An ordered counter. How do you make one of them? It's actually only this line that makes the ordered counter. I inherit from counter and ordered dict. I am guaranteeing a particular order of calls where the underlying dictionary comes last. So when a counter uses its default supplier of mapping services, its default supplier for mapping services is dict, which is unordered. We're telling it to use another supplier, ordered dict, and it's a remarkably easy thing to compose. I went ahead and modified a couple things in the class because you want to give it a nice looking repr so that it looks pretty, and make it pickleable. You do go ahead and polish up all your classes to make sure that they look nice and pickle, right? That's what I thought. We'll go and run this, and presto, this counter has inside it an ordered dict. The ordered dict, remember, it has counted everything in abracadabra. Let me see if I can make that bigger. But of the letters, the A came first, so it's listed first. Then we saw the B, so it's listed second. Then the R, and the C. In other words, these now show in the order that they were encountered. You've made a ordered counter in one line of code. Who thinks super is super in now? Take that, David Beasley. My code is done. You guys could go home. Oh, risk. Let's do more risk. Emacs seems to have worked out well for me. Live demos have worked out for me. Take a bigger risk. Take 3 people who I've never met before and bring them up on stage and have them model all of this for you. What could possibly go wrong? including there's not a lot of stage space, and the lights are pointed right here and not right where they would be. What does super mean? If you take something away from this, it means next in line. Where does the line come from? The linearization algorithm. What do you need to know about the linearization algorithm? You could read a paper on it, or just remember a couple things. Would you just like to know the couple things? Children get called before their parents, and parents get called in the order listed. Up here, who gets called first? The ordered counter, or the counter, or the ordered dict? Who's first? Ordered counter, because children go before their parents. Okay, now, what about the parents? Who comes first, the counter or the ordered dict? Counter. The parents stay in the order listed. There's one other rule for the linearization algorithm, but it's not a particularly, it's important in practice, but not important for you to remember. And that is that the order is stable, and that when these get combined, your parents' orders don't get scrambled. Those three rules put together say ordered counter gets called first, then the counter, then the ordered dict. And our whole goal was to make sure that counter, when it asked for dictionary services, got its supplier from the ordered dict first. Easy peasy. What does super mean? It should have been called the next one in the line. What's the word that means make into a line? Linearization. What are the only things you need to remember about linearization? Children come before parents, and parents stay in order. With that rule, you can force the line to be in the right order. Easy peasy? So it means next in line. Think of that every time you think of super. It does not mean call your parents. Do you think it's pretty easy to talk to the next person in line? Yes. What is cooperative multiple inheritance? Cooperative multiple inheritance is where you design a tree of classes where everybody is cooperating. And what kind of cooperation is required? That everybody says next in line. Is multiple inheritance with diamond diagrams easy or hard? Well, we said if there's no conflicts, it's easy. And we said if it's single inheritance, it's easy. But everybody thinks of the other case as hard. It's not hard. But the It was a battery problem, wasn't it? The article super considered harmful suggested it was a hard problem. I believe it was because the author didn't know the rules. He had a legitimate reason to not know the rules. No one had ever published them. You're about to find them out in a way that's easy to remember. Our problem is this. The only thing we're trying to do when we call super is say, I want the next in line. And what kind of problems can you have with that? Let's observe. May I have my 3 volunteers? This is all unrehearsed. These people don't know me.
That's not true.
Oh, one of them does. One of them knows too much. The stories he could tell. They're kind of arranged in a blob. What should I do to them? I'm going to linearize you. Tomas, here at the end. Merci beaucoup. There you go. They are now linearized. We have a tool in Python that says next in line. What is it called? Super. All right. We'll observe the first problem. All of you have been programmed to call super, which means give it to the next person where?
In line.
Next person in line. How hard could that be? Let's see how Nina does. Nina, hand it to the next person in line. She was quite successful. Hand it to the next person in line. She was quite successful. Thomas, hand it to... Oh, problem number 1. Remember, Thomas can't possibly know in advance who is going to be called, so he has to hand it off. Oops, it's mine now. He has to move it forward. He's required to use super. Okay, I'll just work with the mic. Okay, and so his problem is he's going to make a call to a person who doesn't exist. This was one of the problems mentioned in super considered harmful. Well, you're on stage now. Could I take advantage of you? Yes. How about stand on the other side of Thomas? Okay, whenever I tell you to hand it to the next person, just say, sure, I did it, but don't really do it, okay? Okay? All right. Here we go. Ready? Hand it to the next person. 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 You're just supposed to say, sure, I really did it, but not actually do it. Did that improve the situation? A great deal. So, here's one of your problems with super. You can't possibly know in advance who's upstream. That's determined by your children, not by you. Thank you very much. Okay. Thomas has to hand it off to somebody. But now the person at the end of the chain tries to hand it off to someone who doesn't exist. And in Python, that gives you an attribute error. I know what you're thinking. Hey, nothing broke this time. And the answer is you put a stopper class at the end. Not object. You can create an object called root and put it in, and all it is something that has the method of interest, pass it along, but doesn't actually call super. Somebody at the end of the chain shouldn't have super. Easy enough? All right, next problem. Thomas, to the middle. He seemed amazingly cooperative, but sometimes he's not. We'll see. Pass it along. Pass it along.
No.
I see how it is. One of your problems is that someone along the way doesn't cooperate. Remember, super was designed for cooperative multiple inheritance. So, what do you do if you want to work it with Thomas and he's not going to forward it along? Do you want to volunteer again? Oh, okay. Here you go. I'll put you right here in front of Thomas. Okay, Thomas, step back. Oh, there you go. All right, Nina, come back 2 feet. Okay. Nina's job, her new job is, when I tell you to do work, briefly hand this to Thomas, take it back, and then when I say pass it along, pass it to your left. Ready? Here we go. Nina's very cooperative. Here we go. Nina, do something with the bowl. Okay, take it back. Now pass it along. This is a very simple thing. What do you do when there's a class that's designed, thank you, perfect. When a class is designed non-cooperatively, like Thomas here? The answer is you make another class whose sole job is hand it to Thomas, let him do his work, and then pass it along. Easy enough? Okay. And so one of the problems mentioned in super considered harmful is it doesn't work with classes that weren't designed cooperatively. It does work perfectly. You just have to put an extra cooperating class in front of it, and it's remarkably easy to do. Who learned something new? There's a third problem. Go ahead and line up again. Any order will do. Okay. Take the banana and pass the bowl along. Take the banana and pass the bowl along. Take the banana and pass. What happened? What happened was he got unexpected arguments. In fact, Nina wants a banana, Thomas wants the water, I didn't catch your name actually, and Ashley wants the banana. Remember, none of these people knew each other before this started, so they don't know what to hand to each other. Positional arguments won't do. Somebody was reaching for a banana in the positional argument, and they got the wrong thing. That sort of threw Thomas for a loop. I know what you're thinking. Keyword arguments. With the keyword arguments, I say water equal water, banana equal banana, apple equal apple. Nina, take the banana. Tomas, take the water. Ashley, take the apple. And that covers 100% of the problems mentioned in super considered harmful. Thank you to my volunteers. Okay. Take 2 minutes to wrap up. Learning points there are, when you're using super for cooperative multiple inheritance, use keyword arguments because you can't know in advance who you're calling. And you don't know what arguments they're going to need. They know which ones they need, but they don't know who they're calling in advance. For this to work, you can't have a Thomas in the middle who doesn't pass it along. But you can make a wrapper around Thomas that is cooperative. It's a trivially easy thing to do. Just make a subclass that has a super in it. And remember, this is a chain of calls, and at the end of the chain, somebody has to be at the end of the line and stop making calls. You do that with a stopper class. This is all covered in the blog post. Along the way, you've also learned to make ordered counters effortlessly, how to do dependency injection with mock objects, and how to get pizza that is organic instead of filled with insecticide. Who learned something new? Okay, by a show of hands, we're going to vote. Super or harmful? Ready? How many of you think super is considered super? How many of you think super is considered harmful? My work is done here. Thank you very much for coming to my talk.
We have time for a few questions if you want to line up at the microphone in the center of the room.
I think our work is done here. Thank you, sir. Oh, no, I guess it's not. There is a question.
Hi there, thanks for your talk. Being a naive Python developer, I would put self.member in a class. Can you tell more about when you should use super versus self?
The whole purpose of super is to call the next one in line. That's the position after the first the position line, the current position line. Over here, when we call super, it goes up one level to pizza. Or I'm sorry, starting with pizza, we go up one level to dough factory, and the next one goes to object. If you don't need the next one in line, if anybody in line would do. If you'd like to start over again at the beginning, use self. If you'd like the next in line, use super. Does that make sense? Every time you do self dot, the chain of lookup starts from the bottom and works its way up again. Super says next in line. So in this chain here, if we called self, it would have started all over again. If we called super, it was the next one in line. Excellent question. $5. I don't really pay up.
Check, I'll take a check.
Yes, sir.
Yeah, I basically have the exact same question. So if you have a...
I have the exact same answer. I feel bad about that.
Excuse my ignorance about the super, but sometimes I see super used with arguments inside it. Is that only a Python 2 thing versus Python 3 thing, or?
You can do it in Python 3 as well, and it was so confusing in Python 2 that we put some deep dark magic in Python 3 to automatically compute those arguments for you. So without arguments, it looks beautiful and tends to do the right thing. It's truly magical. But in fact, what do the arguments mean if you did put them in or using Python 2? Basically, we need two things. We need to know Matthew, whose method resolution order are we searching? So we're searching Matthew's. And we need to know where we are right now. So in Matthew's method resolution order, which is all of this, where are we right now? We're at Rachel. So Rachel's super will call the next in Matthew's chain, the person after Rachel. So essentially, this is a computation. Whose line are we dealing with? Matthew's. Where are we in the line? At Rachel. And then super computes the next one in the line, which is Dennis. So it's a computation of two arguments that seem to confuse the heck out of people. Deep Dark Magic has made it go away. Excellent question. $10.
Okay, but I got it right that the
Greedy,
empty
huh?
argument is only in 3, right? In 2 you need to put arguments, or?
Right.
Okay.
And the
thanks.
two arguments are, whose line are we searching? Matthew. And where are we right now? So that we can compute, remember, what super really means is the next one in the line.
Thanks a lot. Great talk.
All right.
That'll be all for questions. Thank you very much again.
All right. Have a wonderful PyCon.